For my project, I took on the role of a product manager tasked with building a model to predict the net hourly electrical energy output of a combined cycle power plant. The business goal is to accurately forecast energy generation to improve operational efficiency and reduce costs associated with over or under production. The first step was to frame the business problem as a machine learning task. And since the goal is to predict a specific number, the megawatts of energy produced, this is definitely a regression problem. Next, I had to choose the right evaluation metric. The most important business consideration is that large prediction errors are very costly. A major underprediction could lead to a brownout. Therefore, I chose root mean squared error, or RMSE, as my primary technical metric because it heavily penalizes large errors by squaring them before averaging. For communicating with stakeholders, I also decided to use mean absolute percentage error, or MAPE, because it's highly interpretable. Saying the model is 99% accurate is much clearer than citing a specific RMSE value. My modeling platform was Google Cloud's Vertex AI. I used its AutoML capabilities, which allowed me to focus on feature strategy rather than custom coding. My initial hypothesis was that not all features were equally important. The dataset provided includes four features: T for temperature, AP for ambient pressure, RH for relative humidity, and V for exhaust vacuum. To find the best model, I decided to compare multiple AutoML models, each trained with a different set of features. This allows me to test which features provide the most predictive value. To ensure a fair and unbiased evaluation, I started by splitting the data, reserving 20% as a final test set. This data would not be touched until the very end. For comparing the different feature set models, I relied on Vertex AI's built-in robust validation. AutoML automatically uses a portion of the training data for validation to prevent overfitting and give a reliable performance estimate for each model. Here are the results from the validation data for my three different models. As you can see, Model 1, which used all four features, T, V, AP, and RH, was the clear winner. It achieved the lowest root mean squared error of 3.397 and a mean absolute percentage error of only 0.586%. A MAPE score this low means the model is approximately 99.4% accurate on average, an excellent result. This experiment also provided key insights. By comparing the full model to the others, I confirmed that while temperature and exhaust vacuum are primary drivers, ambient pressure and relative humidity also add a significant predictive value. Because it was the most performant and used all available predictive data, I've selected Model 1 as my final champion model for this task. The very last step would be to evaluate this model against the unseen test set to get a final, unbiased measure of its performance. Thank you.